Impulse momentum is a third way of solving dynamics problems. We recall from previous lectures that Newton's second law says that the force equals the time rate of change of linear momentum, or ddt of mv. If we rearrange this equation, like this and integrate the relationship, we wind up with the integral of dmv is just the final momentum minus the initial momentum. And so the initial momentum plus the integral of the force over the time interval is equal to the final momentum. This is an expression for the principle of impulsive momentum. It says that a particle acted upon by a force will have a change in momentum. We can draw this graphically, if you will, as a particle having some initial momentum acted upon by a force whose impulse is the integral of the force over the time interval equals some final momentum. So I can draw this vector summation like that. Also, it's frequently written as follows, or we define the impulse, which is a vector relationship going from 1 to 2 or over a time interval t1 to t2 as being the integral t1 to t2 of the force. Now, unlike energy methods and work and energy methods that we saw previously, the principle of impulse and momentum is a vector relationship, which means that we have to take into account the three-dimensional nature of the vectors, magnitude and direction. The next topic concerns impulse and momentum. We know if we have a particle that's acted upon by a force, from Newton's second law, we know that the net force acting on it is equal to the time rate of change of the linear momentum. That's just a statement of Newton's second law. We can separate this and integrate over some time interval. And if we do this, the left-hand side just remains the integral of the force over some time interval, and that's going to be equal to the final momentum minus the initial momentum. Or, stated another way, rearranged, the initial momentum plus the integral of the force from t1 to t2, some time interval, equals the final momentum. This is the statement of the principle of impulse and momentum. It simply says, and the initial momentum plus the impulse, this is called the integral of the force over time, equals the final momentum. In fact, sometimes we abbreviate that integral as simply the impulse from 1 to 2, that is the impulse of the force from time interval going from 1 to 2, that's just equal to this integral. So that's the principle of impulse momentum. Something important about it is that this is a vector relationship. So in the last topic, when we were dealing with work and energy, we had scalar relationships, but now we're back to vector relationships similar to Newton's second law. So since we have a vector relationship, now, in order to get solutions to problems using the principle of impulse and momentum, we have to consider components. So, for example, in Cartesian coordinates, we have three components, x, y, and z. We can write three independent equations from the principle of impulse and momentum in each of the relative directions. Now we can also choose other components if we wish. Typically it's going to be, we will usually choose x, y, and z, but as we'll see in some cases, other cases, we will choose other components. We'll get to that later. Sometimes we're dealing with systems with more than one particles, and you can write a principle of impulse and momentum for a system of particles. So you can, for example, I can write the sum over the system of the initial momentum plus the sum over the system of all impulses equals the total final momentum for the system. Now, as we saw with work and energy, it's also true that internal forces, impulses, cancel out. So when writing the principle of impulse and momentum for a system, any interaction forces between particles, their impulses will cancel out. As an example, let's suppose you're in a boat with a rope and that's tied to another boat. If you pull on the rope, right, you will exert an impulse that equals the integral of the force over the time. But at the same time, of course, there's an equal and opposite force acting back on you, whose impulse is the integral of f dt. So they are equal and opposite, and therefore if we wrote the principle of impulse and momentum for the system, the impulses of those two forces, the tension in a rope, would cancel out. One more important aspect of the principle of impulse and momentum is that if the total force is zero, now this is the total force on a single particle or a system, you can say it for either one. If the total force is zero, then the total impulse is going to be zero. In that case, momentum is conserved because the principle of impulse and momentum reduces to mv1 equals mv2. So the initial momentum equals the final momentum. So again, that's true for a single particle or a system of particles if the total force is zero. Okay. Now another interesting thing is that when we look at components, for example, if we look in Cartesian components, if that's the x direction, and we also have an expression for the y direction, right, and we'll say it's a two-dimensional problem for now. Now, if we know that the total force, for example, in the y direction is equal to zero, but it is not equal to zero in the x direction, then in this case we can say that momentum is conserved only in the y direction. So you can have a situation where momentum is conserved in a particular component direction, but not in others. That happens from time to time as well. Now, if we're in a situation where forces are very large and happen over a very short period of time, for example, a bat hitting a baseball, then we call that impulsive motion. And one further thing is, if the forces are large, like a bat hitting a ball, the force between the bat and the ball is going to be quite large, and it happens over a short period of time. What we can do is, during that time interval, that short period of time, you can neglect or ignore non-impulsive forces, or forces whose net impulse is much smaller, for example, gravity. So when you're dealing with a bat hitting a ball, you can write the principle of impulse and momentum over that period of time And since the time period is very short, we can assume that the force is constant over that time period. So the impulse reduces to F delta t. That equals mv2. So we can write the principle of impulsive momentum this way and ignore non-impulsive forces like with a bad hitting ball gravity. Sometimes this is convenient, particularly, as we'll see in the next topic, when we're dealing with impact. So impact is just the collision between two bodies over a brief period of time. There's some nomenclature we need to get out of the way. So assuming we have two particles, here's particle A and particle B, and maybe it's two tennis balls bumping together, two hockey pucks on ice, two billiard balls rolling on a table and bumping into things like that. So if we have two particles A and B, and they're bumping into each other, the first important aspect is identifying the line of impact. The line of impact is defined as the common normal between the impacting surfaces. So in the case when we're dealing with these two balls bumping into each other, right, the tangent to the surfaces is this line, and perpendicular to that is this line, which is the line of impact as it's labeled here. All right, and it's important that you be able to identify the line of impact in problems like this. Next is the idea of central impact. Central impact is the case, as we've seen here, when the center of gravity, CG, of both bodies lies on the line of impact. Central impact is always going to be the case when we're dealing with particles. Later, when we deal with rigid bodies, we may have instances where the center of gravity of a body is not on the line of impact. In that case, it's called eccentric impact instead of central impact. The next situation is direct impact. Direct impact is the case when both velocities lie along the line of impact. And so that's the case in this picture. The initial velocity of particle A is along the line, as is B. Okay? The other case is called oblique impact. That's when the velocities are not along the line of impact. That's the case in the second picture. Here the initial velocity is not along the line of impact. And so two situations we'll deal with now with particles are direct central impact. That's when the CG of both bodies is along the line of impact and the velocities are along the line of impact. The second case is oblique central impact. Again, the CGs are on the line of impact, but the velocities are not. So let's consider the case of direct central impact, where two particles are colliding and their velocities are along the line of impact. So in this picture, here we see the line of impact as it's coming, two particles moving with different velocities. Okay? So let's look closely at the process of the collision. First, we have the two particles moving with different velocities before impact. Then the two particles come together, and imagine they are two tennis balls to make it easier, and they begin to come together and the two bodies deform. They compress, right? And at some point of maximum deformation, right, the two particles will be sort of stuck together, if only for an instant, and moving at the same velocity that we'll call u. And then those two will begin to regain their normal shape, eventually come apart, and reach their final velocities after impact. Okay? So we have this period of deformation when the two bodies begin to compress, followed by what we've referred to as restitution. when the two bodies spring back to their original shape. This all is happening sort of during the collision, in between when they first come into contact and when they come apart. Okay? Now, if we were to write the principle of impulsive momentum for the system of particles, right? Now, starting just before impact until just after. First of all, there are no external forces, so the momentum of the system is conserved. So that's the expression for conservation of momentum. However, notice that since we have direct impact, all of the velocities are along the line of impact. There's not going to be any lateral velocities, so all of the motion is in a straight line. So it reduces to a one-dimensional problem. So we can write it as a scalar relationship. And note that I used VA and VB for the velocities before impact, and VA prime, VB prime for the velocities after impact. That's common notation for the collision process. Well, for the normal analysis problem, we're presumably told what the mass of the two particles are, we know what their velocities are initially, and we want to find the velocities after the collision. So we have two unknowns, but we only have one equation, and that one equation is this conservation of momentum for the system statement. So we need a second equation. Well, the second equation comes by looking carefully at the collision process. So if we write the principle of impulsive momentum for a single particle now during the collision process, let's split the collision process itself into two parts. One is the deformation period, which is shown in this top graphic. We have an initial momentum of the particle. Then there's the period when it's deforming, okay, and the individual particle has an impulse on it from the other particle. And then you've got some velocity after the deformation forms, but this is in the middle of the collision process when the two particles are stuck together with a common velocity u. The second half of the collision process is restitution. The individual particle begins returning to its original shape, so it begins with the momentum with the common velocity u. There's an impulse acting on the particle that in this case we'll call r, acting on A by particle B, because again we're writing principle of impulsive momentum for a single particle, right? And then eventually it comes out with its final velocity after the whole collision process, right? So we have we've split it again, let's split the collision into two pieces, the deformation process and the restitution process. And this leads to the definition of the coefficient of restitution. This comes from the fact that it's not necessarily true that the restitution impulse is equal to the deformation impulse. They may not be equal. E is the coefficient of restitution, and it's defined as the restitution impulse divided by the deformation impulse. So if I write the principle of impulsive momentum for particle A during deformation and restitution, if I write the principle of impulsive momentum for particle B alone during deformation and restitution, and using this definition, it leads to the final result, without going into the details, this equation, which is called the restitution equation. So now we have two equations relating the velocities before and after impact. One is the restitution equation, and the second is our conservation of momentum equation that we saw previously. So now, given the initial velocities of the two particles, the masses of the particles, and the coefficient of restitution, E, we can find the final velocities. There are a couple of special cases that are worth considering. The first one is the case where E is equal to 0. This is the case where the impact or collision process is perfectly plastic. Okay? And so the result of the restitution equation with E equal to 0 says that VB prime has to be equal to VA prime. That is, the velocity of the two particles after the collision are equal. Or in other words, they stick together. They bump into each other, the two particles bump, and then they move as one afterwards. Okay? And so, to solve the problem, it reduces to a single equation. The conservation of momentum equation becomes the initial system momentum equals the final system momentum. The second case is when E is equal to 1. I forgot to point out that E is always going to be between 0 and 1. All right, so the minimum of value is 0, the maximum is 1. When E is 1, that's a perfectly elastic collision. So the restitution equation becomes that. So the relative velocity is the same before and after impact. And so we can use this equation in combination with our conservation of momentum equation to solve the problem. Okay. Something interesting about this case, when it's perfectly elastic, is that energy is conserved for the particles. Okay, conservation of energy is not necessarily true. In fact, it is not true when E is not equal to 1. Next, let's consider oblique central impact. This is the case where two particles collide and their initial velocities are not along the line of impact. So in this case, we define a component system. And we call them, somewhat unfortunately, normal and tangential. The normal direction is just the same as the line of impact. So here's the line of impact. It's also the normal direction. So it's the normal to the two contacting surfaces. And then perpendicular to that, we have a tangential direction. Okay, and so we use this component system when splitting up the components of the vectors. As you'll see in a moment, it's a convenient way to split it up. Okay, so assuming, as before, we know the initial velocities, we know the masses, and we know the coefficient of restitution, we want to find what the velocities are after impact. Now in this case, this is a two-dimensional problem. They're moving in a plane, so each vector afterward has a tangential and normal component. So essentially that means we now have four unknowns: the tangential and normal components of velocity B, the tangential and normal components of the velocity of A. So we have four unknowns. We need four equations to solve the problem. So having defined the normal and tangential directions, we want to first look at the principle of impulsive momentum for a single particle. And we want to write this principle of momentum for each particle individually in the tangential direction. So let me draw you a picture. If this is particle A, here is the normal direction, and here is the tangential direction. And drawing the free body diagram of it, the only force acting on it is the impulse force by particle B on particle A. And that force is in the normal direction. There can't be any lateral forces exerted by this impact. So there's the principle of impulsive momentum in the tangential direction for particle A, all right? But the tangential force is equal to 0. So what we have is momentum is conserved for particle A in the tangential direction because there's no force that way. And since the masses are the same, they cancel out, and what we find is that the initial velocity of particle A in the tangential direction equals the final velocity of A in the tangential direction. Well, that's convenient. We can do the same thing for particle B and we'll get the same result. So there are two of the four equations we need to solve the problem. Essentially, for each particle individually, momentum is conserved in the tangential direction, okay? And so there's no change in the tangential velocities after impact. They're the same before and after impact. The next thing we want to do is write the principle of impulsive momentum for the system. In the normal direction. And since the only forces on the system are internal forces, the two impulses between the balls, their impulses cancel out, and so momentum for the system is conserved. So we have the initial momentum of the system in the normal direction has to equal that of the final momentum. This is exactly the same as what we saw for direct central impact. Along the line of impact, in this case we're calling it the normal direction, momentum of the system is conserved. That's our third equation. And the final equation comes from looking at restitution, again in the normal direction. So the restitution equation applies in the normal direction, and that's our fourth equation. So when we're solving problems of oblique impact, in the normal direction, back to my picture, in the normal direction we take the components of the velocity in the normal direction and we treat the problem just like direct central impact. So we have momentum in the normal direction for the system is conserved, and we have restitution in the normal direction. In the tangential direction, right, we know that the velocities don't change at all because momentum is conserved for each individual particle in that direction. And so that's how we solve oblique impact problems. Now let's look at impact problems where one of the particles' motion is constrained. So in the picture you see here, we have a block that's sliding along a surface. And so this block, we know that its motion is only going to be horizontal. It's not going to move up and down. Its motion is constrained. A ball that's bumping into it, however, is unconstrained. Okay? And so the velocities of the ball are oblique relative to the line of impact. And again, we define the normal and tangential directions from which we can write some equations. But also, in this case, we're going to have to look at the x and y directions, as we'll see as important as well. These are tough problems because it's mixed component systems. You're going to have to write some equations in the normal and tangential direction, some equations in x and y, and it's going to be mixed in these kind of problems. Okay? So here we have a ball bumping into the block, and the block is moving horizontally along the surface. Okay? So one thing we know about the block is its motion is going to be solely in the x direction, not in the y direction. So we're down to three unknowns: the x component of velocity A and the normal and tangential velocities of ball B. Okay? We know that the velocity of block A in the y direction is 0. So we need three equations. So what we want to do is first we want to look at the principle of impulsive momentum for each particle, right, separately, and then the principle of impulsive momentum for the system. Alright, so let's look at the principle of impulse and momentum for both particles. Let's start with the ball. Here's a free body diagram of the ball. The only force acting on the ball is the impulsive force by the block on the ball. Remember, we're dealing with impulsive motion, so during the collision process we can ignore gravity since it will be relatively small. So here's the force, and we know that that force is entirely in the normal direction. In this case, the normal direction is perpendicular to the face, the angled face of the block. Okay? So let's look at the principle of impulse and momentum for the ball alone. And first, if we look at it in the normal direction, right? In the normal direction, there's a force, there's an impulse acting on the ball. And we don't know that force, so we can't really do anything with that equation. However, if we look at the principle of impulse and momentum for the ball in the tangential direction, we know that there isn't any force. So how about the principle of impulse and momentum for the ball in the tangential direction? Okay, so that equation says that the mass of B, which is the ball, times the velocity of B, right, the impulse is 0 in this direction, so there's no impulse, so that's just going to equal the mass of the ball times the velocity of ball afterwards. So in other words, momentum is conserved. Sorry, I forgot to put my T for the tangential direction. So momentum for the ball is conserved in the tangential direction. This is just like the tangential result we saw for oblique impact, right? And so in other words, the velocity of ball tangential before equals the velocity of the ball in the tangential direction after. So there's one of our equations. Now if we look at the block alone, the principle of impulse and momentum. So we don't know the magnitude of F. We know its direction but not its size. We also don't know the magnitude of the reaction force, the ground holding the block up, right? So we don't know the direction of the net force, right? So for the block, we can't identify a direction for which momentum is conserved. We can't find a direction where the force is 0. So there's no identifiable direction for the block where conservation of momentum is conserved. And that's what we're looking for when we write impulse and momentum equations for collisions. We want to know directions or situations in which momentum is conserved. So we can't go any further with that. So next, since we're done with writing principle of impulse and momentum for individual particles, let's write the principle of impulse and momentum for the system. Okay, so now let me go back to my system. I'll draw a new free body diagram. So here is my system, right? And I want to write the principle of impulse and momentum for the system. So here's my system. There's internal forces here. Their impulses will cancel. But I also have this reaction force, which is the force that imposes the constraint, if you will. Now I don't know the size of this, but I do know its direction. There's no friction for the block sliding along the ground, so that force is entirely perpendicular to the surface. So the only force external to the system is this reaction force, and we know that it acts in a y direction. So that means perpendicular to that, in the x direction, there is no external force on the system, so momentum is conserved. So we conclude that momentum for the system must be conserved in the x direction because there's no net force there. So we can write that conservation of momentum. The mass of A times the velocity of A in the x direction. Mass of B, velocity of B in the x direction. That's the initial system momentum in the x direction. And so there's our conservation of momentum equation. So you see what I mean earlier when I said we are mixing component systems. Our first equation was written in the tangential direction. Now we've written an equation in the x direction, and it's okay to do that. We just identified the direction in which momentum was conserved for the system. And now we've got one final equation we need, and that is the restitution equation. And the restitution equation always applies on impacts in the normal direction. So writing out restitution in the normal direction, and there we have our three equations to solve this problem of constrained impact. First, we know that the ball momentum is conserved tangentially. Second, we know that momentum is conserved in the x direction for the system. And third, we know restitution applies in the normal direction. And that's enough information to solve the problem. But we do have the work of determining components in two different directions. We have to split the velocities up in normal, tangential, and x and y directions as well. Okay. So in general, for these constrained impact problems, so when you're solving these problems, first you look at the unconstrained particle and you find the direction for which momentum is conserved. That's always going to be the tangential direction, right? So for the unconstrained particle, tangential to the line of impact, right, perpendicular to the line of impact, the momentum will be conserved. So you can find that component of velocity. The second thing you do Second, you write the principle of impulsive momentum for the system perpendicular to the constraint force. Right? So on this problem, we wrote the principle of impulsive momentum in the horizontal direction because we know the constraint force was vertical. Okay? That constraint force isn't always going to be vertical or necessarily horizontal. It could be at an angle or something. Find the direction that's perpendicular to that constraint force and write the principle of impulsive momentum for the system, because momentum will be conserved in that direction. And finally, you write the restitution equation in the normal direction. And that's how you do these constrained motion problems. You really can simplify it with these three steps. The hard part is going to be identifying those key directions. The tangential direction, right? The direction perpendicular to the constraint force. It may not be simply a horizontal or vertical. It could be some other direction. And finally, identifying the normal direction where you can apply the restitution equation.